Hello SLifeX community! This is a simple project called STM32 Data Graph. As you can see, by rotating the left-hand side potentiometer, the value of the left-hand side graph changes accordingly. This is true for the right-hand side graph as well. By touching the right-hand side graph, it gets wider, so you could see it better and track the changes of the graph better. We can also see both graphs simultaneously and compare them by touching that little button down there. As you can see, when I rotate the potentiometers simultaneously, the graph's value changes accordingly. So we can see both graphs simultaneously and compare their values better. Well, explanation is enough. Let's get down to business and implement this simple project. Requirements for this project are STM32F7 Discovery Board, 2 potentiometers and some jumper wires, TouchGFX software, and CubeIDE. Let's run TouchGFX. Here is where we set up our GUI. Select Create New, search STM32F7, and select the Discovery Board. Choose a name for the project. I'm going to call it Data Graph. And then choose a location to save your project. Folder name cannot contain spaces, so I'm going to use underline. Our setup is almost done. Let's create it. I'm going to choose box for the background. Expand the box to cover the whole background and set the color to black. It's good, let's save it. I'm going to add dynamic graphs to the project, and by using these widgets we're going to display the data on the display. Adjust it as you wish. Of course we're going to change it in minutes. Adding another dynamic graph for the second ADC. Adjust it. It looks good. Now I'm going to add a flex button. It helps me to change the screens and set it somewhere like here. Yeah, it's good. Let's go to the properties of the first dynamic graph. Location, graph area margin, and graph area padding are fine, leave it as default, but set the dynamic behavior to scroll. Data points 100 is good, and set the maximum value range to 3300 millivolts. This is the maximum voltage that our graphs are going to show. Level of precision 1 millivolts is going to be good. In line here, in fact, you can change the color and the line width and the opacity. I'm satisfied with the color and line width, so I leave it as default. Vertical grid lines, major division. It divides the page, and you can see it helps us to see the data better by default. And the interval is 10, and I'm satisfied with the light blue color, so I leave it as default. But the alpha, in fact, it is the opacity. If it is 255, it makes the graph so nasty. Something around 72 might be good. Yeah, it's better. Do the same for the horizontal grid lines. Go to major division, and by default the interval is set to 10, but because I changed the maximum value range to 3300, it changed the interval to 330, and I'm satisfied with it. Just change the opacity to 72. And the other settings, just leave them as default. Let's do the same for the second dynamic graph. And be careful about the naming, we're going to use it in minutes. when we're programming, dynamic behavior to scroll not and over right and other things. Set the maximum to 3300 and major division. Set the alpha to 72 and do it for the horizontal grid lines as well. $72, yeah. Let's save the project. So far we're satisfied with it. Let's choose an image for the button. Go to image. No image is added to the project. I have some images in my computer, so I'm going to add them. I'm going to add these two buttons to the project. You could access these images in my GitHub repository, which the link is provided below in the description. Just go to TouchGFX folder, assets, images, and these are the images that I used in the project. You could download them and use them. After adding the images to the project, here you can access them. I set the light button for when it is released and the dark one for when the button is pressed. Adjust the button as you wish. It may be good. Let's delete the box. Now it looks better. Set it in the middle. Fine. Let's save it. Adjust the dynamic graphs. Now it looks better. Let's choose an icon for our button. Go to icons, select it, and here you can see so many different icons. I'm going to use stack. Select it. As you can see, its name is a stack line chart. Let's change its position. For X, something around 48 might be good. Yeah, I'm satisfied with it. Fine. Now it looks better. Maybe it's better to be a little bit higher. Let's change its Y position. Yeah, it's a bit better. Let's save it. We're satisfied with the project so far. This button simulates the GUI you have designed. So let's simulate it. Now we can see how the button works. I don't like its icon when it is pressed. So let's change it. Pressed. And yeah, this one is better. I'm going to use it. So I add it. Simulate it. Now you can see the image is changed and I'm satisfied with it. Let's change the color of the second dynamic graph. Go to Elements, Line. In oscilloscopes, usually light blue and yellow is used. So I'm going to do that. Yeah, I'm going to add it. Copy the color code. I want to change the color of the grids as well. So I'm going to vertical grid lines and paste the color code. Blue changes to yellow. Yeah, it's better. And do the same for the horizontal grid lines as well. Brilliant. Let's save the project and create the code. This button in fact generates the code. Simulate it. Now it looks better. Let's change the name of the screen and set it to main. This is going to be our main window. Then add another screen. Let's call it stack screen. We're going to shoot two dynamic graphs in this screen. Copy the elements of the main screen and paste it in the stack screen. And we don't need the flex button with this view here, so delete it. And adjust the dynamics graph in a way that you could compare the graphs. As you can see, the graph is a little bit nasty because of the grid lines, so let's delete them for both graphs. Now it looks better, but we need something to be able to compare the graphs in a more precise manner, so let's add the grid lines just for the top dynamic graph. I'm going to choose white color for it. For white color, you need to enter 7 Fs. This is the color code. Do the same thing for the horizontal grid lines. Yeah. Now let's decrease the opacity to 72 alpha. Now it looks better. Let's simulate it. I like it. Now let's create a mechanism to be able to go to stack screen from the main screen. For that, we need to create interactions. Flex button is already set in the screen. Now we need to set the interactions. Go to interactions, add interaction, and trigger. Set the trigger to button is clicked. And as far as we have just one flex button here, so there's just one option for us, and there's just one click source. So we choose it as it is, flex button 1, then set the action to change screen. We want the screen be changed whenever the button is touched. And choose a screen, go to stack a screen whenever the button is touched, and set the transition to slide and transition direction to east. Whenever the button is pressed, the screen moves towards east. Yeah, let's simulate it. You see, now we are in the stack screen. Now let's create a mechanism to be able to go back to main screen. For that, create a flex button in the stack screen, adjust it to cover the whole graph, add interactions, set the trigger to buttons clicked, and there's just one click source, action change screen, go back to main screen, set the transition to slide, and set the transition direction to west. So whenever the button is pressed, or generally the whole background, the screen moves towards west. But as you can see, nothing is visible here. We need to set the alpha of the flex button to 0. You see, now everything is visible. Simulate it. Now we can come here and go back. Great. Now let's add screens for channel 1 and channel 2 ADCs and set their names as channel 1 and channel 2 as well. Save it. Copy box and the relative dynamic graph for channel 1. Yeah, adjust the dynamic graph. In channel 1 screen, we're going just to show the dynamic graph 1 and channel 1 ADC. Let's add a flex button to be able to enable the transition. So go to interactions, set the alpha. You see, as far as the flex button is not the top element in channel 1 graph, whenever the screen is touched, in fact dynamic graph is touched, not the flex button. So in order to correct that, set the flex button as the top element of the channel 1 screen. Now it is on the top. Save it, go to interactions, add interactions, set the trigger to button is clicked. Click source is flex button 1, this is the only option. And set the action to change screen. And go back to main screen. Set the transition to a slide. And set the transition direction to west. So whenever the screen is touched in channel 1 screen, the screen moves towards west. Save it. Let's simulate it. Right? Oh, we need to set a mechanism to be able to go to channel 1 screen. So come to main, create a flex button, adjust it to cover the whole dynamic graph 1, go to interactions, add interaction, trigger button is clicked. Be careful, here we have more than 2 options. So it is important to select the correct click source. which is flex button 2 in this case. Set the action to change the screen and go to channel 1 screen. Slide and east. Set the opacity to 0 and simulate it. Now it is alright. Let's do the same for the second ADC. Set a flex button to cover the whole dynamic graph 2. Set the alpha to 0. Interaction, add interaction, set the trigger to buttons clicked, and the click source is flex button 3. Change the screen. Go to channel 2 screen and set the transition to slide and east. Alright, let's simulate it. You see, now we are in channel 2 screen. Let's customize the channel 2 screen. Copy a relative dynamic graph and a box and paste it here. Adjust the dynamic graph. Save it. Let's create a flex button. To be able to go back to main screen, set the alpha to 0. Button is clicked. Change the screen. Go back to main screen. Slide towards west. Alright, let's simulate it. Well, our GUI is ready. And there's just one more thing I would like to discuss here. As you can see, some random values are generated by the dynamic graphs whenever they are triggered for the first time. This is not our intention. We just want the dynamic graphs to show the ADC values. This is our only intention. So uncheck generate random values for all the dynamic graphs in all the screens. Well, now I can say that our GUI is complete and ready. And you see, no random values are generated. Let's configure our project by using the CubeMX. For that, we need to go to Files. And by default, we are in the TouchGFX folder, but we need to be in the project folder. So go there, and here you can select the IOC file. Well, here we are. The very first thing that we need to do is going to System Core, RCC, and make sure the high-speed clock is set to Crystal Ceramic Resonator. This is the clock source of the microcontroller. This is already done by the TouchGFX. This software has done it for us. Then go to System and make sure that debug is set on serial wire. Close this panel, go to Analog ADC3. I'm going to enable ADC3 channel 0 and channel 4. If you ask me why I'm doing that, then my answer is if you refer to STM32 F7 Discovery Board user manual, you can see that connector CN5 is dedicated to analog pins of the microcontroller. ADC3 channel 0 is PA0 of the microcontroller and a 0 pin of the Arduino header, which is available on the Discovery Board. And ADC3 channel 4 is a PF6 pin of the microcontroller and A5 pin of the Arduino header. In fact, by doing this, I am enabling the ADCs of the first pin and the last pin available on the Discovery Board, and they're connected to ADC pins of the MCU. Then I go to Parameter Settings, leave the clock prescaler to default, and resolution is 12 bits, of course. It is mentioned in the datasheet of F7 microcontroller. And as you can see, the scan conversion mode is by default disabled. It needs to be enabled. But before that, we need to specify the number of conversions. I set it to 2. This is the number of ADC channels that I want to activate. If you come back here, you can see that scan conversion mode is enabled automatically. This star here indicates that you have changed the settings somewhere else, and these options have been changed automatically to help you configure the project properly. And discontinuous conversion mode is disabled. A scan conversion mode needs to be enabled whenever you want to activate multiple ADC channels, and discontinuous conversion mode needs to be disabled, so the conversions are done one after each other repeatedly. Then I'm going to set an external trigger for the ADC, so it is done in the background without occupying the CPU. I'm going to set the external trigger conversion source to timer 1 capture compare 1 event, and external trigger conversion edge is sensitive to rising edge. As you can see, it is reading trigger detection on the rising edge. In determined periods, the ADC does the conversion. I'm going to set rank 1 to channel 0 and sampling time to something around 15 cycles. We must select cycles in a way to create a balance between accuracy and speed. More cycles, more accuracy, less speed. Less cycles, more speed, less accuracy. But as far as our sensors are potentiometers and their values are changed by human hands, we are not dealing with pretty fast sensors, and their value is not changed so fast. So 15 cycles, not only it is enough, but it is so fast. It is okay for the project. And rank 2, I set it to channel 4 and 15 cycles. And we are done in the ADC. Let's configure the timer. This is the trigger of the ADC. I'm going to set channel 1 to PWM generation channel 1. Here I need to determine the update frequency by setting the prescaler and counter period. To do that, I need to know the frequency of the timer 1 clock. As you can see, here is written that APP2 timer clocks is set to 216 MHz. How do I know timer 1 is connected to APP2 bus? Then if you refer to datasheet of this microcontroller, you can see that timer 1 and its PWM is connected to APP2 bus. So go back to CubeMX and you see APP2 timer clocks is 216 MHz. Going back to pinout and configuration, I'm going to set the prescaler to 216-1, counter period to 1000-1. In this manner, in fact, I am creating update frequency of 1 kHz. How did I do the calculations? As you can see, the update frequency equals to timer clock divided by prescaler plus 1 divided by period plus 1. Timer clock was 216 MHz. I set the prescaler to 216-1. So the second statement in this equation equals to 216. And I set the period to 1000-1. So in this equation, the third statement equals to 1000. Let's go back to CubeMX and let's do the calculations. The clock was 216 MHz divided by prescaler plus 1, which equals to 216. Divided by counter period plus 1, which equals to 1000. And as you can see, the update frequency is 1 kHz. So this was the way that the calculations were done. You go to PWM generation channel 1 and set the pulse to 1000 divided by 2. In fact, I'm setting the duty cycle to 50%. And as you saw, the ADC was sensitive to rising edges. So I need to create rising and falling edges so the ADC can detect them and does the conversions. There is just one thing. You may encounter strange errors when you want to open the CubeMX from the TouchGFX software. If you want to prevent those errors from happening, Xcube TouchGFX pack must be installed. You can see that in software packs, manage software packs, ST microelectronics. Scroll down to reach Xcube TouchGFX, and if the box is green, so you know that this pack is installed successfully. Installation of this pack is not the topic of this video. So we're done here. Clock configurations, we already checked it. And project manager, TouchGFX has already selected the name for the project and selected the IDE and the location, so we don't need to change it. Code generation, copy only the necessary library files. And in advanced settings, because we are using DMA, so this DMA should be configured here, and it should have a high priority. Here you cannot see the DMA initialization because we did not configure it. So let's go back to pinout and configuration, analog, ADC3, and DMA settings. Whenever you want to activate multiple ADC channels, you have to enable DMA settings. Select Add ADC3, set the mode on circular mode so the conversions are done one after each other repeatedly, and make sure memory is checked. And data width, half word is enough for our project as long as we are going to use unsigned 16-bit integers. And going back to project manager advanced settings, now you can see that DMA is initialized successfully and it has a high priority. So we're ready to generate the code. Let's do it. The use newly reentrant must be set in order to make sure the newly is fully reentrant. Free RTOS advanced settings. Do you still want to generate the code? Of course not. I want to enable this setting, so I select no. Pinout and configuration, go to system view, find free RTOS, advanced settings, and here you see that this option is disabled by default, so we're going to enable it. Now let's generate the code. Open project. These files are related to my previous project. I need to close them. You want to import the new project? Of course, I want to import the new one to the workspace. And I just want to exclude the previous project from the workspace. Successfully imported the project. Brilliant. Let me just close the last file related to previous project. In here you can reach min.c file in application, user, core. Let's go to ADC3 init, and you can see the ADC resolution is set to 12 bits as mentioned earlier, and the scan mode is enabled. These are our CubeMX configurations, and the external trigger is set to timer 1 channel 1, and the number of conversions is set to 2. Now let's go to timer 1 initialization, and by pressing Ctrl and clicking on MX timer 1 init, you go to its definition, and you see the pre-scaler is set to 216 minus 1, and period is set to 1000 minus 1, and the pulse is set to 1000 divided by 2, so everything is alright. Just before our main function, I'm going to declare two arrays, raw values, and this array has two variables. In fact, I'm going to store ADC raw values in this array, and I'm using 16-bit unsigned integers for both arrays. I'm going to make it volatile, so its value is not changed by the compiler if any optimization implementations are going to take action, and creating another array, and I'm going to call it voltages. In fact, in the callback routine, I'm going to change the raw values to voltages by multiplying it and dividing it by numbers that you will see in minutes. Let's save it. In the while loop, just before the while loop, I'm going to write code. Always write your codes between code begin and code end. Thus, whenever you update your CubeMX file and generate the code, your codes are not cleaned by the code generator. Be careful about that. I'm going to start the timer. In order to do that, go to drivers, HAL driver, and find team.c file. No. I'm going to use the function HAL team pwm start. Search pwm. To do that, press Ctrl F, and in the string finder write pwm and press enter until you reach HAL team pwm start. Here it is. By using this function, you start the PWM of the timer that you configured in the CubeMX file. So copy this function and paste it here. The first argument is reference of HTeam1 in our case, and the second argument is timer channel 1. Great. Now let's start the ADC. To do that, in drivers find adc.c file, and here you have to find HAL ADC start DMA. Here it is, and because we want to start our ADC in the DMA mode. Copy this function and paste it. The first argument is reference of HADC3 in our case, and the second argument is the array or the variable which we are going to store our ADC values. In our case, this is array because we want to store multiple ADC channels values. Write raw values, and length is 2. This is the number of ADC channels that we are going to use. Let's save it. Great, 0 errors, but 2 warnings. One warning is RWX permissions. It is ignorable. In fact, by building it again next time, you could get rid of this warning. But what is the other one? It says incompatible pointer type. As you saw, we declared these variables as unsigned 16-bit integers, but this function is created in a way to accept 32-bit integers as inputs and arguments. So I cast it to uint32, and don't forget the star because we're working with arrays and pointers. So let's build it again. Great. And by building again, you get rid of RWX permission warning. I told you it is ignorable. Now let's declare our callback routine. To do that, again go to ADC and find HAL ADC conversion completed callback. And as you can see, this is a weak function, so you can override it. Copy this function, paste it, and in the function body, I'm going to write voltages equals to raw values multiplied by 3300 millivolts. I'm going to show the values in millivolts and divided by 4095. How did I calculate this number? Here you can write 2 to the power of 12. Why 12? As you saw, our ADC resolution was 12 bits. That is why we write 2 to the power of 12. It equals 4096. As long as we start from 0, so this number must be 4095. But remember, we're not working with a single variable. We are working with arrays. So I create a for loop, and I equals 0 until it is less than 2. Increase I each time, indexed voltage, and indexed for the raw values. Let's build it. 0 errors. So I'm going to, in fact, ADC values are stored in raw values, and I changed these values in voltages so we can understand it. We're done in the main C. We just have to pass these values to the GUI so we can see them. To do that, we need to go to user, GUI, and as you can see, for each screen that we created in TouchGFX, 2 files is created, presenter.cpp and view.cpp, and another file which is called model. So let's go to model and go to model listener.hpp. Here we need to declare virtual functions. Virtual void update graph. This is for the first dynamic graph, and another virtual void for the second dynamic graph. Then we need to include TouchGFX HAL types.hpp. We are done here. And in the model CPP file, we need to include STM32 F7 XX underline HAL.h. So I can use the drivers, and I need to extend the voltages array so I can pass these values to GUI and use them here. In model tick, write model listener update graph and pass the voltages index 0 to this model listener. And again, write model listener update graph 2 this time and pass it the voltages index 1. This is for the second dynamic graph. Close it. Now we need to configure every screen that we created in TouchGFX in the CubeIDE. Let's start by main screen. Go to main presenter, then go to main screen main presenter.hpp. Here you need to declare functions. Update graph for the first ADC, int value, another update graph, save it. Then go to CPP file. Here you need to define the functions here. Update graph. In the function body, we need to write view.update graph and pass the value to it. Defining the other function, update graph 2, int value 16-bit. And the function body, write view.update graph 2 and pass the value. Now we need to go to main view. Go to the HPP file, and again in HPP files we need to declare the functions. Void update graph, int value, and update graph 2. Then go to the CPP file and define the functions here. Update graph, and in the function body write dynamic graph 1.add data point. We are updating the value of the first dynamic graph. Do the same thing for the second dynamic graph. So the second dynamic graph is updated as well. Save it and close it. Let's build this. Oops, 22 errors. Well, it says that no declaration matches update graph 2. Maybe in the HPP file I did not declare it. Yes, this might be the problem. Oops, here I forgot to write 2. In the main view HPP file, when you declare functions, because we're working with different widgets, we need to declare different functions with different names. Be reminded, in TouchGFX, for each widget, you need to declare different functions in the CubeIDE or in your debugger, generally in your IDE. Build it again. 18 errors this time. The errors reduced, but still they exist. What is that? Update graph cannot be overloaded. Maybe I did the same thing in the model listener.hpp. Yes. And let's build it again. Brilliant. 0 errors. And this warning is ignorable. We need to repeat this procedure for every screen that we've created. Let's continue by the stack screen. Go to stack presenter, stack presenter.hpp. Declare the functions here. In this screen, like main screen, we want to show both dynamic graphs. So we declare 2 functions. The first one is update graph and the second one is update graph 2. Go to CPP file and define the functions here. For the first update graph, in the function body, write view.update graph and pass the value to this. Then the second function is update graph 2, and in the function body we write view.update graph 2. Then we need to go to stack view, and the HPP file, declare the functions here. The first one is update graph, and the second one is update graph 2. And in CPP file, define the functions. In the first body function, write dynamic graph 1 dot add data point. And this function adds the new data to the dynamic graph and updates it. And the update graph 2 in the function body, we write dynamic graph 2 dot add data point and pass the value to this. Our stack screen is configured as well. Brilliant, 0 errors. Now we need to go to channel 1 and then go to .hpp file. Again, we're going to declare the function. Our work here is just repetitive because we've created multiple channels. And in the CPP file, in the function body, write view.updateGraph. Then we need to go to view file. In HPP file, declare the function, updateGraph. And in the CPP file, define the function. And in the function body, write dynamic graph 1 dot add data point. And be careful, in this screen we're just showing the first dynamic graph. So we just declared update graph and we defined update graph in CPP files. Because we're just going to show one of the dynamic graphs, which is the first one. Well, our channel 1 screen is configured as well. There's just one left, and that's channel 2. Before that, build it. Great. Go to channel 2 presenter, then go to its HPP file. And just before the private, declare the update graph 2 function, because we're going to show just the second dynamic graph in this screen. And in the presenter.cpp, define the function, which is view.updateGraph2. And in the view file, go to HPP file, declare updateGraph2, and in the CPP file, define updateGraph2. And in the function body, write dynamic graph2 dot add data point and pass the value to this. Build it. Well, all of our screens are configured. This is our simple circuit for this project. We are going to use 2 potentiometers. One side of each potentiometer is connected to 3.3 volts, and the other side of the potentiometers is connected to GND or ground. Then the middle pins of potentiometers are going to be connected to pins PA0 and PA5 respectively to read the analog data. Here you can see the components that are going to be used in this project. 1 breadboard, STM32 F7 Discovery Board, 2 potentiometers, and some jumper wires. Here you can see the potentiometers. The side pins are going to be connected to VCC and GND, and the middle pins are going to be connected to analog pins of the microcontroller. Mount your potentiometers on your breadboard. Then connect the side pins of the potentiometers to positive and negative rails. As you can see, make sure to connect them properly because breadboard pins are so close to each other. Then connect these rails to 3.3 volts and GND pins of the microcontroller. But before carrying on, as you can see in the right side of the board, different power supply modes are available. External 5 volts, USB SD-Link 5 volts, USB full speed, and USB high speed. For this project, I'm going to use USB full speed. Then connect those rails to 3.3 volts and GND pins, as you can see in the power header of the microcontroller. Connect the red wire to 3.3 volts pin and the black jumper wire to GND pin. Great. Then connect the middle pins of the potentiometers to PA0 and PA5 of the microcontroller respectively. Brilliant. Then, for providing the power supply of the microcontroller, I'm going to use a micro USB cable. Connect one side of the cable to CN13 or connector 13 for USB full speed, and the other side to your laptop. As you can see, when you connect the cable to your laptop, the backlight turns on. Then I'm going to connect the on-board ST-Link of the microcontroller to my laptop by using A to B USB cable. Connect one side of the cable to CN14 or connector 14 or USB ST-Link, and the other side to your laptop. As you can see, when you connect the ST-Link to your laptop, a window pops up, which means your laptop has recognized the ST-Link successfully, so you can exit this window. And here is the result of what we have done in our project. I hope you have enjoyed the journey of implementing this project, and this video have been useful for you. Don't forget to like and subscribe this video if you enjoyed it, and stay tuned for more videos. Good luck!